All right, welcome to the video on weight. This section in Shankar deals with a very specific problem, which is basically the same as our example problem right here. But before we talk about this one in particular, I just want to mention a few facts about weight and the normal force, just because they're going to be so important in talking about, in using Newton's laws. Okay, so weight is the same thing as the gravitational force. Weight equal to gravitational force. So we'll have different letters for this. We might use W for weight. We might use FG for gravitational force. The interesting thing about this is that it's proportional to the mass of an object. Right? So the gravitational force on me and the gravitational force on my older brother, who's a little larger than me, will not be the same. Right? So G is going to be what we're used to from our acceleration due to gravity. So G is 9.8 meters per second squared. So what we already saw for the kinematics, from the kinematics problems. And then M is going to be the mass of our object. Right, so if the mass is in kilograms and G is in meters per second squared, then SI units times SI units will give us SI units on the left, so that'll be newtons. Kilogram meter per second squared is a newton. Right, so we have newtons is equal to 1 newton is equal to a kilogram times the meters per second squared. You could write this however you'd like. Kilogram meters second squared. So if you had an object, so if suppose we drop an object, free body diagram of an object in free fall. Free fall. Okay, so so I jumped off a cliff and I am fallen. There's only one force acting on me. Okay, weight, or the gravitational force, will be the only force in this class that will be a non-contact force. So every other force in this class is going to be because something's touching something else. But the Earth pulling on us doesn't need to be in direct contact with us. So it's the whole mass of the Earth and the mass of me. It's these two that attract one another. Right? So the Earth is actually pulling me down, and that's exactly what this weight is. So this gravitational force is mg. So I could put a W there, I could put an FG, I could put mg. Right? Sometimes as a shorthand we just put mg straight on the free body diagram. Okay, so our free body diagram only has one force. And then separately we can use Newton's second law to determine that, okay, so say this is the plus y direction. Okay, so sum of the forces in the y direction equals mass times the y component of acceleration. So here there's only one force. So the sum of all of the y components of the forces, there's only one of them, and that's mg. Except if the y direction is upward, then the gravitational force is going to have negative y component. So we would plug in just a single minus mg on the left-hand side. And this should be the same m. Same mass, it's my mass, MAY. So it looks like we have AY equals minus G. So we're seeing that this statement that the gravitational force is mg is equivalent to saying that an object in free fall will have acceleration due to gravity negative g. Right? Taking the positive direction to be vertically upwards. Okay, so you might see it written that way. You might see it A is equal to G in magnitude vertically downwards. I ran out of room right there. So keep in mind that is, this is perfectly fine if you have specified a coordinate system, but maybe you want to write it like this, just to make it clear. In case someone didn't see that you wrote that right there, that you defined the plus y direction to be vertically upwards. You could write this, and everyone will agree with this no matter what. Acceleration is g. So we specified the magnitude and then comma specifying the direction as well. Right. Now the second most common force that you should be familiar with is the normal force. Right. So probably the most common situation that you have is not an object in free fall like that, but you just standing on the ground. So if you're just standing on the ground, you always have the weight acting down on you. So there's always mg down, even if you're at rest on the ground. It's not like the Earth knows that you're on the ground and turns off or anything. Okay, mg is still downwards. But you don't crash into the ground because the ground is pushing back up on you. So if the ground wasn't there, you would fall downwards. But the ground is preventing that because it's pushing upwards on you. So this normal force, so normal means perpendicular. The normal force is the force perpendicular to a surface. In this case, the ground is a surface, and the normal force is perpendicular to that plane. Okay, so the ground is a two-dimensional thing, and then the direction perpendicular to that and away from the surface is the normal force direction. So it's the force perpendicular to a surface, and it exists because the object is preventing you from crashing into it. So microscopically, this is a result of the molecules just are bound together and they refuse to break apart. So you can think of it as springs. You have a bunch of these springs connected together, and then you're standing on these things. And these are really strong springs, so that they might deform a little bit, but you're not breaking them at all. So overall, instead of these springs connecting like this, you're going to deform them a little bit. So this spring is pushing back this way, the spring is pushing back this way. When you add the two, it overall pushes upward, and it's just preventing you from crashing through it. Okay, so this is a contact force. And it exists because the surface is strong enough not to break. Right? If it wasn't, then you would break through it. So the normal force is existing because it's just preventing the material from breaking. Right? And so you don't crash through the ground. The ground pushes back up on you because it can. Right? Okay, so I think at this point we're ready to analyze motion in the elevator here, because the only two forces acting on you are, there's always a constant mg downwards, and then the normal force is you can sort of work backwards and figure out what the normal force is if you knew the acceleration, or vice versa. So we're going to use Newton's second law to infer what's going on with the normal force, or maybe we know what's happening with the normal force and we can figure out what's going on with the acceleration. Okay. So in this problem, we have a person standing in an elevator. So this will be the original problem. So remember, the free body diagram is always going to help us with these problems. I mean, free body diagram, don't resist drawing these. These show that you know what's going on with the problem, and it makes the problem a whole lot easier. Right? Mg is always vertically downwards. That's probably the first force that you should be drawing on any free body diagram. And then the person standing in an elevator, so the person isn't touching the ceiling or anything. They're standing on a scale in the elevator, and the scale is able to push back up on the person. So the scale is pushing up on the person. This normal force is going to be the reading on the scale. Right? The scale is reading your weight because you're pushing down on the scale is pushing up on you, and it's that direct contact force that it's reading out. All right? So now, separate from the free body diagram, we can set up our Newton's second law equation. Sum of the forces equals mass times acceleration. And in this problem, think about what we know. Do we know the sum of the forces? Do we know the acceleration? What do we know? Keep in mind pounds is another unit for force. It's not an SI unit. It's the unit you're probably more used to. Right? So we know that this mg is what the person normally weighs. So what that means is that if you stood on a scale not on the elevator, then the scale reading is going to read exactly what your mg is. So we know that John normally weighs 180 pounds. So the mg for John is 180 pounds. But the situation in the elevator has the normal force only 150 pounds. All right. So it looks like if the downward force is 180 pounds and the upward force is 150 pounds, there's overall a net force downwards. All right, so let's introduce a coordinate system here. So this will be my plus y direction. Looks like the sum of the forces is in the negative y hat direction. So this will be minus, so what we're really doing is we're specializing to we're just looking at the y components. So this is no longer a vector equation, but a y component equation. This is minus 30 pounds equals m ay. And I don't like this unit of pounds, but I can kind of do a trick here to get rid of this pounds. I can multiply and divide by g. So I have ay in terms of g. So I'm going to divide and multiply by g. And mg is 180 pounds. So negative 30 pounds is equal to 180 pounds times ay over g. Now this is nice because it says that ay looks like negative 30 over 180. It's about negative 1/6, or negative 0.17 g. Right, so that was one of the original questions, right? What is the acceleration of the elevator? Looks like it's 0.17 g in the downwards direction. So this is vertically downwards. Acceleration is vertically downwards. So John is moving downwards. In addition to, so these are two separate things. We're told in the problem statement that John is moving downwards, and then separately from that, we know from this problem that he's accelerating downwards as well. So John must be speeding up, right? The velocity is downward, and in addition, so that's from the problem statement, and then in addition, the acceleration is downwards. So these two facts together mean that John is speeding up. All right. So you've probably been in an elevator before. So pretend you're at the top floor of a building and you're going to go down in floors. So you get in the elevator. You're on the top floor, you get in the elevator, you press the ground floor. Right after the doors close, do you feel lighter or do you feel heavier when the elevator first starts to go? You probably know just from experience that you feel lighter, right? So this is exactly what's going on in this situation. So normally you weigh some amount, you're going to feel a little bit lighter. So the feeling that you have, where you feel a little bit lighter in that situation, the reason for that is that the normal force pushing back up on you needs to temporarily go down in order for you to accelerate downwards. So remember, the point is for you to get in the elevator, and the point is for you to move downwards. So you have to accelerate downwards in order for you to go from the top floor to the ground floor. Now you can't change the magnitude of your weight. So what happens is that the normal force temporarily goes down. So the elevator is moving down because of some cables. So, you know, there's heavier machinery going on that determines that. And then in response, because the elevator is moving down, this is going to go down so that you stay along with the elevator. Right? It's not moving downwards so quickly that you separate from the bottom of the elevator, right? The elevator still needs to push up on you. It could be the case that the elevator rope breaks, in which case, this can just completely disappear, and then you and the elevator are both moving downwards at 9.8 meters per second squared. But you would definitely feel that. That's different than most elevator rides, right? So John's speeding up. This is at the first moment when he's moving down. So you could probably also reason what's going to go on right before John gets to the ground floor. This n is going to have to increase to something beyond mg in magnitude in order for John to slow down and come to rest. So he's going to feel a little bit more massive than he normally does. And you know this from an elevator, right? When you get to the ground floor, you feel a little bit heavier for a moment right before the doors open again. Okay? So there's a way to analyze this using Newton's second law. So your book goes over that. This is just, so this W that is in your book is talking about apparent weight. So I would be a little bit careful with, I might put a subscript for W apparent, because other textbooks will just write W for the gravitational force, which is constant. And your book is making it sound like the weight is variable, which it is if you're talking about apparent weight. Which is what we're talking about if you weigh yourself on a scale here. So yeah, your book talks about it maybe a little bit differently. It's talking about the apparent weight, or in other words, they're solving for the normal force. So let me compare with Shankar here. So the equation we have here is that the normal force minus mg is equal to ma. And so what I'm calling the normal force is what your book is calling weight. And notice how we can write this normal force as m times a plus g, and this is exactly what your book is doing. So your book's calling it W for apparent weight, but really what it is the normal force. It's the force that's pushing up on you. That's not the Earth's gravitational force. Okay, so if you knew, pretend in another problem you knew the acceleration, you could solve for what the normal force is. Okay, and this is taking the vertical direction to be upwards. That's why we have this specific combination. So if n is positive and mg is negative, that's assuming that this is the positive direction. Okay, so this is ay, where y is that vertically upward direction. So you can be a little bit more careful than what Shankar does in the book right here, just by specializing the components and being a little bit careful with the terminology, weight versus normal force. Okay.